Hi everyone, this is Wen. Today is July 22nd, 2018, and this will be the third video to talk about the workflow executor. And from last 2 weeks, we were talking about logistic regression and linear regression and multivariable linear regression. And today we're gonna continue to talk about one of the supervised learning algorithm in machine learning that is very popular. And compared to both logistic regression or neural networks, the SVM sometimes gives a very cleaner and also powerful way to learn complex non-linear functions. And actually, based on logistic functions, we can do a little bit modification and then get a SVM loss functions. And so firstly, let's review a little bit about the logistics regressions we talked about a few weeks ago. So here is a hypothesis function of the logistic function. And basically, this is a sigmoid function and will give out the theta transform times x. And based on this hypothesis function, and we will get logistics loss function like this. So from this function, we can see there will be two parts. And firstly, this is yi times a minus log function includes a hypothesis function, and also this part. And basically, if y equals 0, and this part will be 0. And if y equals 1, and this part will be 1. And the summation of the m item from I equals 1 and will be the value of the loss function. And we will try to get the minimum value of this loss function. So based on this function, we can do a very little modification and then get the SVM loss function and compare these two functions, and we can see that basically this part is substituted by the theta transform times x, and to get substitute the log function. So, and also we will get instead of 1 over m, we will times c variable, and this variable is what we're gonna determine. We will have to choose the value of c, and basically if c is large, and this function or this algorithm will give a lower bias and high variance. If it is small, c, and we will get higher bias and no variance. So this is a basic idea of the c value. And also we can see that actually we have two types of usage of SVM algorithm, and one is without kernel like this, and we only plug the theta transform times x, and we also can substitute this part as a kernel. And for example, the very popular usage of the kernel in SVM is Gaussian kernel, and we can put the function of Gaussian function here, and then maybe we can make another video sometime later to talk about the case to get the kernel version of the SVM, but this time we will stick with the nonlinear or without kernel version of SVM. So this is the loss function of SVM without kernels. So we can see that if it is larger than 1, and this part is equal to z. So we can see if it is larger than 1, it will be 0 for the cost t1 function, and if it is less than -1, the cost t0 function will be 0. And so basically it's more complex function compared to logistic function, but we will use this function, loss function, to put in our program today. And another very brief introduction of the hypothesis function of the SVM, and it's very clear about straightforward. If the theta transform times x larger than 0, we will count it as 1, otherwise it will be 0, because it's a classification and classification problem. And let's talk about this function a little bit more. If c is very large and comparable to this theta square summation, and so this part will be the determine the final value of the loss function. So we also call that as a large margin function or large margin problem. That is to draw a line, a linear line between the different parts and get the largest margin. So overall, this is a basic idea of the SVM function and algorithm. So let's get into and take a look at the code of today. So this is a main method, and as before, we will initialize instance new task T1, and we will call the class of SVM regression function class, and then to new instance of this class and put into T1. And we have few catch exceptions here, and then we will read the files iris1 txt and then iris2 txt as a training. This will be the training set, and this will be the testing set. And basically, this time we will use a iris dataset to test and to train and test our SVM algorithm. So finally, we will put the data into the output file, and later we will run it and then output the function execution is complete. So let's take a look at the SVM regression file. And in this file, basically it's roughly the same, much similar to the logistic function, because logistic regression algorithm, because it's quite similar. And also we will declare this class and extend the task class, and we also define a vector of vector as x as a matrix, and to put all the training data. And we also have a y as a vector to keep all the outputs. So let's take a look at the data we have. So this is a training data set, and we have 1, 2, 3, 4. We have 4 dependent variables and 1 independent variables at the last column, and we have 2 categories, and basically it's 0 and 1. And finally, we have a testing data file, and with 1 records, and we will predict whether this is category 1 or 0. So let's go back to the SVM regression file, and let's keep looking. So here we define all the vectors, matrix, and the variables to stand the length of x or y. And we will define the SVM function constructor. Here is super. Super is a to get a method in the task class and to define the name of the function and also the description. And we will get the input file, ins and outs, as put into the array, and then to read the data. And I think we have do that in before. And firstly, we will get a matrix file and also the vector files for y, and we will get the file name. Basically, we'll get the path, and then we use this read matrix from file method and to read the path of this file, and then to get to the parse to the X matrix or vector of vectors, and then we will get the test value to put into the vector test X, and also we will count the Y size and also the size of X. And let's keep looking. So here is we will start to training the data, and here we will get the initialize the theta array, and firstly we will put the value as 0.1 for each of them, and we will call the gradient descent function. And basically the gradient descent function will, as before, it will adjust the theta by the learning rate, and we also will call the hypothesis function and to get the difference value from the actual value, and then to compute the delta theta value, and then to change the delta value based on this learning rate times delta theta. I think we would talk this before, so maybe we can go back and keep looking the code. So basically, I just introduced that we have to choose two things. The first thing is a C value, and second thing is a kernel for the SVM model. And here we only choose one of these because we use a linear kernel SVM. Based on the C I choose, I put in the J loss function. So let's take a look at the J first. So in this function, we will create the formula as we showed a few minutes ago to describe the loss function of the SVM algorithm. So here we define few variables like the loss, results, and cost T1 and cost T2, and also the hypothesis function. And in the hypothesis function, we will return 1 or 0 based on the theta transform times theta transform times X. So it will get the summation of each of them and then determine whether it is larger than 0 and returns 1 or 0. So here we see the hypothesis function we calculated, and we will get the result 2, because we will use this function, this result, to determine what the cost T1 and cost T2's value, as we saw in the formula. So here we get the cost T1 either equals 0 or either equals minus result 2 plus 1, and for cost T2 it's the same. And then finally we will calculate the loss function based on these two, cos t1 and cos t2, and then we will get the last part of the theta square, and to sum them up, and we will get the final loss function. So let's go back to the wrong parts. So basically, we will check learning rate will be this point 0.0001, and then we will determine if the j function is less than a specific value, and then we will break. And I just said that based on the choose of the c value, and we will get different variance and bias. So as far as I choose same value as a logistic function, and I try to get the best learning convergence, and I can only reach close to the 0.35 value, but it still gives me a good prediction of the result. So let's take a look at this function. So let's run this program. So it starts to learn. Okay, so it gives us a result of the iris2 file, and it's classified as 0, and it's indeed as 0. And we can test one more about, we copy one value in the class category 1, and then to do a little bit change based on the value. And save it, and then we go back to main and run it again. And wait for a few seconds, and we will see the value. Yeah, so it still predicts the correct type of category. So we can do one more. Basically, let's do 1, 0. So let's go back to this file and do a little bit change based on the value. Okay, go back to the main. Just a few seconds, and will give us the result. Yeah, it still predicts the correct type of category. So I suppose we successfully get the theta value, and that is able to fit our model and do the correct prediction. So basically, this is this program talk about. So and one more thing I hope to mention is that the optimization problem of SVM is a convex optimization problem. So that means it will always have a global minimum value. So that helps us to confirm we have, not like the neural networks, we have a local minimum value, but for the SVM we can always get the global minimum. So that is a good part for this kind of cleaner way to do the machine learning, to deal with some complex nonlinear functions. And maybe in future we can continue another video to talk about injecting a kernel like the Gaussian kernel into the SVM algorithm, and that could be more complex and more interesting. So this will be the content of today's video. And until then, happy coding. Thank you for your time.